In this question, we want to know about multicollinearity. When does this problem occur? The problem of multicollinearity occurs when independent variables are highly correlated with one another. So what we want is for the x's to relate to the y's. We don't want the x's to have relationship with one another. And when they have relationship with one another, if this relationship is strong, we have the problem called multicollinearity. So the answer here is C. Multicollinearity occurs when independent variables are highly correlated with one another. In the quadratic regression model, we want to know what happens when the sign on beta 2 is whether greater than 0 or less than 0. Now, beta 2 is what determines the direction that the parabola opens up. So if the sign of beta 2 is less than 0, the parabola will open downwards. So A is incorrect because it says if beta 2 is less than 0, the parabola will open upward. So A is incorrect. Now if beta is greater than 0, the parabola will open upward. So the best answer here is B. When beta is greater than 0, the parabola open upwards. For the following regression equation, a unit increase in x1 while holding x2 constant at a value of -4. So if x2 is held constant at a value of -4, it basically means x2 is -4. So we can plug in -4 into that regression equation. And when we simplify that, we obtain y hat equals 80 plus 4x1. And this is now a simple linear regression equation, which we can interpret like we are interpreting the value of the slope. So this 4 here just basically tells us that if x1 increases by 1, y will increase by 4 on average. The answer here is A. For a given simple linear regression model, the width of the confidence interval for any xg and alpha equals 0.05 will be... Now let's first take a look at the confidence interval for the simple linear regression model. I'm going to start with the ends at the bottom here. So the ends at the bottom here tells us that as the sample size n increases, the width of the interval will become narrower. So for example, it will be narrower for a larger n than for smaller n. So that makes C incorrect because C says it will be wider for a sample of 64 than a sample of 36. No, it's the other way around. It's also wrong for D. D says it will be narrower for a sample of 25 than a sample of 36. No, it should be wider because the bigger the sample size, the narrower the confidence interval. So let's look at A and B for alpha equals 0.02. The first thing to note here is that alpha equals 0.05 means 95% confidence. And alpha equals 0.02 means 98% confidence. So in essence, when alpha is 0.05, we have like 95% confidence here. So the width of the interval is pretty much just that. But when it is 98%, we have a wider width of the interval. So in essence, the confidence interval will be narrower for 95% than for 98%. So the answer to that question is A. It will be wider for 98%, which means it will be narrower for 95%. So it will be narrower when alpha is 0.05 than when alpha is 0.02. Which correlation coefficient shows a stronger linear relationship? 0.75 or -0.70? So we know that correlation coefficient is represented by R. We also know that if R is close to 0, the relationship is weak. So the farther R is from 0, the stronger the relationship. So obviously here, the relationship is stronger for 0.75 than for 0.7. We really don't care about the sign, positive or negative. If it is stronger, it will have a higher absolute value. So if we consider between -0.9 and 0.6 here, so we can say that it will be stronger again for -0.9 than for +0.6. So It is the absolute value that we look at when we're talking about strength, about correlation coefficient, and not the sign on the value. So the answer here is B. Here we're looking at donors. We have data from 5 donors here, and we have their tax deduction rate and this year's donation. So we're looking at a relationship between their deduction rate and their donation amount. And then we're told that the estimated sample regression model is this given over here. The question here wants us to find the residual corresponding to donor 3. So to find the residual corresponding to donor 3, we first calculate the y hat value for donor 3. So we plug that into this formula and say donor 3, y hat is going to be, so we have 110 plus 1000 times 0.2. So we plug that into the equation. So y hat will give us 310 for donor 3. Then we can find the corresponding residual by subtracting y minus y hat. So we're subtracting y here minus y hat, and that's going to give us 40. So here we have the same question. However, the question requires us to find the sum of squares errors. So sum of squares errors is given by this formula. Sum of squares error is SSE. So in essence, we need to find y minus y hat, square them, and then sum them. So first, we have the y hat here. We have the y minus y hat for every observation, and then we square them. So all we need to do now is sum them, find the total. The sum of squares errors, or sum of squares residual, is going to be found by obtaining the totals of those numbers. And if we do, we obtain 2000. SSE is going to be 2000, so the answer is A. So here we're looking at the same question. We already found the SSE. Now we want the standard error of estimate. So the standard error of estimate is just the square root of SSE over n minus 2 for simple linear regression. So we're looking at square root of 2000 divided by 5 minus 2. And that will give us 25.8199, which is not one of these options. So the answer is none of the above. In number 9 here, we want to find the rejection region. Based on the information given to us, we're given the value of the test statistic, which we really don't need. We're given alpha, which we need. However, we don't have the degree of freedom. So the sample size or the degree of freedom is not given to us. So it is not possible to find the critical value that determines the rejection region from the t-table if we don't have the degree of freedom. So the answer here is cannot be determined from given information. If the correlation is 0.9, the percentage of variation in the dependent variable not explained by the variation in the independent variable is. So first we need to know what that definition is, the percentage of the variation in the dependent variable not explained by the independent variable. So the percent of variation explained is r squared, but the question is asking for the percent of variation not explained. So 1 minus r squared is what we need here. Now we're told that the correlation coefficient is 0.9. We know that r squared is the square of correlation coefficient, which will give us 0.9 squared, and that is 0.81. So 1 minus r squared is now going to be 1 minus 0.81, which is 0.19. So in essence, 19% of the variation is not explained, and the answer is E. The difference between the observed value of the dependent variable and the value predicted using estimated regression equation is known as the. Now, the observed value is y, the value predicted is y hat. The difference between them, obviously here, is called residual. For a regression model, which of the following inferences can be drawn from the scatter charts below? E is the errors and X is the independent variable. Now, one thing we can see here is that as the value of x increases, we see that there is a pattern in the errors or residual. So we can see a funnel pattern or increasing pattern. Any pattern like that is not acceptable. And when we have a pattern like that, we say we have a condition called heteroscedasticity. So heteroscedasticity means the variances are not constant, or the standard deviation of the errors are not constant, or the error variables don't have a constant variance. So variance not constant. That's the variance of the error. It's not constant. So we can say we have a varying variance. The variance varies, is not constant. If the variance is constant, we say we have homoscedasticity, which is what we want. So heteroscedasticity in this case is a violation of that requirement. So the answer is A. In 13, for a regression model, the following scatter chart will help us conclude that. Now, the first thing we need to note about the scatter chart is that we have a T at the horizontal axis here. And when we have a T there, it means we have time series data. Okay, so, and on the vertical axis here, we have an E, or the errors, or the residual. So, in essence, we're testing for the independence of the errors. Whenever we plot time against errors, we're testing for the independence of the errors. Now, if there is no pattern in this plot, then we have the independence. But in this graph, we have up and down variations, which is a pattern, and that's what we don't want. Whenever that happens, we say we have autocorrelation. So that is a violation of the independence requirement. So that autocorrelation basically says we violated the independence requirement, so the errors are no longer independent, they are dependent. So the best answer here is C, that is, the errors are interdependent or dependent. In a simple regression analysis, y is dependent, x is independent. If the y-intercept is positive, what does that tell us? For example, if we have y hat equals 4 minus 3x. Now, 4 is the y-intercept and is positive. What does it tell us? It doesn't tell us much anyway. It doesn't give us much information because the y-intercept does not really tell us much. Of course, we can see that the slope is negative here, and some of the things we can conclude is that the correlation coefficient is also going to be negative if the slope is negative. But this guy doesn't tell us much. So if y-intercept is positive, there is a positive correlation, no. If x is increased, y must also increase, no. If y is increased, x must also increase, no. So none of these alternatives is correct if y-intercept is positive. If slope is positive, then we can say as x increases, y also increases on average. We're talking about the y-intercept here, which has nothing to do with the slope. So the answer to this is none of the above. This regression model is, okay, first if you look at A, it says first order model. So this is not a first order model because we have some terms with squares here. So it is not a first order model. B also says first order model, so that is also out of the question. D says second order model with 6 predictor variables. No, we don't have 6 predictor variables here. We only have 4 predictor variables. We have x1, x2, x3, and I1. Those are the 4 predictors here. And again, it's not a third order model. So it's only a second order model because the highest power of the x's is 2. So the best answer here is C. We have a second order model with 6 independent variables. The independent variables is determined by the number of betas that we have here apart from the intercept, of course. So to determine the number of independent variables, we just count the number of betas here. We have 6 terms apart from the intercept. So the answer is C. In 16, the percentage of variation in the dependent variable which is explained by the regression model is measured by the So this is a very important definition. R squared is what we're talking about here. R squared is the percent of variation in the dependent variable, which is explained by a regression model or explained by a variation in the independent variables. So the answer to this one is R squared, which is the coefficient of determination. Here we have an ANOVA table, and we want to find the value of the adjusted R squared. There are a couple of formulas we can use. We can find R squared easily here. Okay, we can find R squared by using 1 minus SSE over SST. SST, which is the sum of y minus y bar squared, SS total. So we have those two values here. We can find them and then use the adjusted R squared formula that has a relationship with R squared to calculate it. So first thing we need to do though is maybe just quickly fill up the missing number because they're pretty easy to fill out here. Since we must have a total of 60 here, so 60 minus 6 is going to be 54. So the same thing to find SSR here, we just subtract SSE from SS total. And to find MSE here, we just divide SSE by DF of E. So the adjusted R squared can be found by another formula, which is this one here. So we have all these items given to us. This is our SST here. So we just need to throw them into the formula and we will obtain our adjusted R squared. And we have negative 0.9109 for adjusted R squared. So like I said, this is not the only way to do it, but it's just one of the ways. And the answer is C. So here we have the same question, but this time we need the standard error of estimate. So which is pretty straightforward to calculate. Standard error of estimate is SSE over n minus k minus 1, the square root of that, or just the square root of MSE if you like. So we'll throw that into the formula and that will give us 1.1789. So the answer is B. Which of the following conditions is primarily associated with time series data? So with time series data, the particular error we're checking for is independence. We want to see if the plots are independent when we plot the errors against the time value. So we want just points all over the place. We don't want any specific pattern. So we say the errors are independent. Now if the errors are not independent, we say the errors are serially correlated or autocorrelated. So if they're not independent, we say they are serially correlated or autocorrelated. So in this case, the answer here is going to be D. And by the way, we check for all these anyway whenever we are determining whether the assumptions are satisfied. So the answer here is just autocorrelation because we're dealing with time series data. The standard error of estimate SE is D. So we know the formula for standard error of estimate is square root of SSE over n minus k minus 1. And then we know that SSE over n minus k minus 1 is just the square root of MSE. So the answer here is D. Standard error is the square root of MSE. 21. The dash is a measure of the error in using the estimated regression, that is, we're using y hat to predict y in a sample. So the measure of the error when we're using y hat to predict y is what we call residual. So when we do y minus y hat, we are calculating the residual. In a regression and correlation analysis, if r squared equals 1, so one of the formulas we have for r squared is 1 minus SSE over SS total, which is the same thing as SSR over SS total. So one of the ways r squared can be 1 is if SSE equals 0. So if SSE here equals 0, then r squared is 1. Or if SSR and SS total are the same. Now, SST equals SSR plus SSE. So if SSE is 0, then SST equals SSR. Or if SSR equals SST, R squared will be 1. So the answer there is D. Here we have a simple linear regression equation, and we're given SSE and SST. We can find our R squared by taking 1 minus SSE over SST, which will give us 1 minus 510 over 1,000, and that will give us 0.49. So R squared is 0.49. We know that R is the square root of R squared, but that could be positive or negative square root. So in this case, we're looking at plus or minus 0.7. Now, we know that as the slope goes, so goes R, and we can see that the slope in this equation is negative 6. So R will also be negative. And the answer here will be negative 0.7 and not positive because the slope is negative. So the answer here is A. Here we have a regression analysis. Y is in thousands of dollars and X is in dollars. This is the resulting equation. And what does this tell us? So normally, if X and Y are both in dollars, we will say if X increases by 1, then Y will increase on average by 6. But because Y is in thousands of dollars, then Y will increase on average by 6,000. That is $6,000. So the best answer here will be D. An increase of $1 in advertising is associated with an increase of $6,000 in sales. The effect of the different levels of a qualitative variable. So we know qualitative independent variable is also nominal independent variable, can be modeled in multiple regression by using, obviously when we're modeling nominal variables, we're using indicator or dummy variables. Indicator or dummy variables is how we model them. So all these other terms are incorrect. So the answer is C here. Dummy variables or indicator variables, which we also call 0-1 variables sometimes. Which is not an assumption of a multiple regression model. So one of the assumptions of the error variable, we want the errors to be normal. We want independence of the error variable, especially with time series data. We want homoscedasticity, constant variation of the error variable. We do not want autocorrelation at all, positive or negative. We want independence, which is the opposite of autocorrelation. So we don't want autocorrelation of the error variable. The answer is A. In a multiple regression model, which of the following is correct regarding the values of the adjusted R squared? Now, adjusted R squared is R squared adjusted for N and K. That is for the sample size and the number of independent variables. And because of the way it's calculated, sometimes so adjusted R squared is often calculated 1 minus N minus 1 over N minus K minus 1, and that times 1 minus R squared. So it is possible for it to be negative because of this formula, because depending on the value of K that we have, or value of N sometimes, this here can be greater than 1. And in that case, adjusted R squared could be negative. So it doesn't have to be positive. It has to be larger than multiple R squared. No, most of the time, adjusted R squared is less than R squared. It can be larger than 1, not usually, but it can be negative. So the answer is A. Multicollinearity between independent variables is serious when the correlation between pairs of independent variables is dash. Now, we are only looking for correlation between independent variables. So we don't want the correlation to be strong. And as we said before, if correlation is strong, we are close to -1 or close to +1 if it is strong. So if the correlation is 0, yeah, that's what we want. That means we have no multicollinearity. If it is substantially greater than 1, it is not possible for the correlation to be greater than 1. So when it is close to ±1, that's a strong correlation, and that is the problem of multicollinearity. All of the following are desirable outcomes for a multiple regression model except, so low 1 minus r squared. Now we want r squared to be high or large. That's a desirable outcome for a multiple regression model. So if 1 minus r squared is low, that is good for the model. Large MSR. Now we want f to be large, so large f statistic will make us reject the null hypothesis, and we will say the model is valid or useful. So if f is large, MSR has to be larger compared with MSE. So large MSR is fine for a good model. Large f statistic obviously is fine. If large MSR is fine, then large SSR is also fine, because MSR is obtained from SSR. So what we don't want is a large MSE. So large MSE here will make f small, and if f is small, we will not have to reject the null hypothesis and the model may not be valid. So the answer here is large MSE. In this question, in a multiple regression analysis, the least squares prediction equation is computed as this. If we hold x2 constant and increase x1 by 2 units, what is the estimated change in the mean value of y? So we're basically just saying, if we hold x2 constant, what will happen to y if x1 is increased by 2 units? Now we know that if x1 is increased by 1 unit, on average, y will decrease because of the negative by 8.6. That is if x1 is increased by 1 unit. Now if we double that, we will be increasing x1 by 2 units, and y will be reduced by 2 times 8.6. So 2 times negative 8.6 here gives us negative 17.2. So which is double the effect of increasing x1 by 1 unit. So the answer to this one here is D. And that concludes this video. Thanks for watching.